Good morning. All right, looks like we have some audio and got my cam. Looks like we're good to go. Okay, so today we're continuing through chapter 4 and we're about to get to ownership and apparently variable scopes, a little bit more code. So this is apparently the part that makes the sort of memory safety part of Rust so memory safe, if that makes sense. Let's hop to it. If you end up watching the VOD for this, please leave a comment during these. If you have any comments or if you're following along, I would love to know. And if you're watching, also just say hi. I would love to say good morning as well. All right, so variable scope. We've walked through an example of a Rust program already in chapter 2. Now that we're past basic syntax, we won't include all of the function main code and examples. So if you're following along, you'll have to put the following examples inside of main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than a boilerplate code. As a first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Let's say we have a variable that looks like this. Okay, so like this looks, makes a lot of sense for other languages too. Avaris, hello, good morning. Welcome to the stream. Let s equals hello. The variable s refers to a string literal where the value of the string is hard-coded into the text of our program. The variable is valid from the point at which it's declared until the end of the current scope. Listing 4.1 has comments annotating where the variable s is valid. So, let's see, s is not valid here. Well, right, because it hasn't been defined yet. S is valid from this point on, and then the scope is over, s is no valid again. A variable listing 4.1, a variable and a scope of which it's valid. In other words, there are two important points in time here. When s comes into scope, it is valid, and it remains until it goes out of scope. Not quite morning over where you are, but you'll take it. What time is it over where you are? Is it afternoon? At this point, the relationship between scopes and when variables are valid is similar to other programming languages. Now, we'll build on top of this understanding by introducing the string type. All right, string type with a capital S. That thing that caused so much fun in that the last few videos. To illustrate the rules of ownership, we need a data type that is more complex than the ones we covered in chapter 3. The types covered in the data type section are all stored on the stack and popped off the stack when their scope is over. But we want to look at data that is stored on the heap and explore how Rust knows when to clean up that data. I guess the big thing is because I sort of went off my own in chapter 3 or at the end of chapter 3, that I kind of forget that they didn't cover string. Germany, it's 3:05 p.m. over there. Awesome. It is 7:06 a.m. over here in Colorado. Let's see. We'll use string as the example here and concentrate on parts of string that relate to ownership. These aspects also apply to other complex data types provided by the standard library and that you create. We'll discuss string in more depth in chapter 8. I think I'm sort of getting an inclination that that borrowing, like the term borrowing, is going to suddenly make a lot more sense in the context of ownership. As in like why they use the word borrowing in that. We've already seen string literals, where a string value is hard-coded into our program. String literals are convenient, but they aren't always suitable for every situation in which you want to use text. One reason is that they're immutable. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For these situations, Rust has a second string type, string. Oh yeah, from stir. This type is allocated on a heap, and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function, like so. So string from. We did this, like we used the string from. Okay. The double colon is an operator that allows us to namespace this particular from function under the string type rather than using some sort of name like string from. We'll discuss this syntax more in the method syntax section of chapter 5, and when we talk about namespacing with modules in chapter 7. This kind of string can be mutated, right, because it's on a heap. Let mut s equals string from hello. Okay, so we've done this plenty in those examples. If you're watching the VODs, I have links to all the examples in the description. All right, so s to push string. So like we're adding this on, we're pushing it to the end, and then hello world. Yes. So what's the difference here? Why can string be mutated but literals cannot? The difference is how these two types deal with memory. So one thing is if I create a stir, like a str, and I assign it, I don't know, 10 characters of memory and only put in 3 of them, can I push 7 more? Would allow me to do that? Or is it just saying like, am I not allowed to create a stir and preset how big it is? Because that's something you can do in like C or C++ or a lot of these other languages. So I would be curious about whether or not they'd let me do that, but I haven't seen any syntax about how to tell it how big it is without actually setting its content. Memory and allocation. In the case of a string literal, we know the contents of compile time, so the text is hard-coded directly into the final executable, making string literals fast and efficient. But these properties only come from its immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable growing piece of text, we need to allocate an amount of memory on a heap, unknown at compile time, to hold the contents. It feels like it's just repeating itself a few different times. That's exactly what it just said previously in the last section. This means, 1, the memory must be requested from the operating system at runtime. 2, we need a way of returning this memory to the operating system when we're done with our string. That first part is done by us when we call string from. Its implementation requests the memory it needs. This is pretty much universal in programming languages. However, the second part is different. In language with the garbage collector keeps track and cleans up memory that isn't being used anymore, and we as the programmer don't need to think about it. Without a garbage collector, it's the programmer's responsibility to identify when memory is no longer being used and call code to explicitly return it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly 1 allocate with exactly 1 free. A stir is a borrowed stir is basically a tuple consisting of a pointer and a length. So there's no information about capacity. So no. Oh, right. I forgot that. So yeah, so it literally doesn't know. Like even if I were to say, oh, you're 10 characters big, by the time it starts to use it, it doesn't know that it's 10 characters big. All it knows is where it begins. And that it... I guess so, because, well, I thought it also had how big it was so that it couldn't go over its limit. But maybe that's string. I'm sort of like getting some of them confused with each other, even though I know that they're very different. But because they're strings and essentially strings, it can be a little bit confusing to me. But I probably just time with it will help out with that. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from listing 4.1 using a string instead of a string literal. Okay, so let s equals string from hello. S is valid from this point forward. Okay. So we're just immediately converting from the stir to a string. There's a natural point at which we can return the memory from our string needs to the operating system when s goes out of scope. When a variable goes out of scope, Rust calls a special function for us. This function is called drop. It's where the author of string can put the code to return to memory. Rust calls drop automatically at the closing brackets. Can I call drop just whenever I feel like it? Note, in C++, this pattern of deallocating resources at the end of an item's lifetime is sometimes called resource acquisition is initialization. The drop function in Rust will be familiar to you if you used RAII patterns. I have never spent any time with C++, so I hadn't actually seen that, but it makes, like, the idea of it makes sense to me. This pattern has a profound impact on the way Rust code is written. It may seem simple right now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables use the data we've allocated on the heap. Let's explore some of those situations now. I also can see, like, if people aren't used to garbage collection, that could also sort of throw people for a loop. But my guess is that with a proper functional programming methodology, it won't really be a problem. And it will make the code a little bit simpler because we won't have to constantly call things over and over and over again. Okay, ways variables and data interact. Move. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer and listing for 2. Let x equals 5, let y equals 5. So, for example, I mean, I know this is a stir. So, like, this should be just, well, will it copy it into a new point of memory, or will it just put a pointer to this point of memory? Listing for 2. Assigning the integer value of variable x to y. We can probably guess what this is doing based on our experience with other languages. Bind the value 5 to x and then make a copy of the value x and bind it to y. We now have 2 variables, x and y, and both equal 5. This is indeed what is happening because integers are simple values with a known fixed size, and these 2 5 values are pushed onto the stack. So yeah, it is doing, like, exactly what most of the other languages are doing. So it's creating another point of memory and sort of assigning that to here. Now let's look at the string version. Let s1 equals string from hello, s2 equals s1. So this, I mean, because they're saying it, like, I'm expecting s2 is now really going to be a pointer, or I guess, like, just like s1 and s2 are not really strings, but really special pointers, or maybe potentially like tuples that hold this metadata that then point to the area in memory with how big it is. That's probably what this is. This looks very similar to the previous code, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2, but this isn't quite what happens. To explain this more thoroughly, let's look at what string looks like under the covers in figure 4.1. A string is made up of 3 parts, shown on the left. A pointer to the memory that holds the contents of the string, a length, and a capacity. This group of data is stored on a stack. On the right is the memory on the heap that controls the contents. So yeah, so it's just this tuple idea where we have the pointer to the beginning of the string on the heap. How long it is, like how many characters, and the capacity, how much it can hold. Representation in memory of a string holding the value hello bound to S1. The length is how much memory in bytes the contents of the string is currently using. The capacity is the total amount of memory in bytes the string has received from the operating system. The difference between length and capacity matters, but not in this context. So for now, it's fine to ignore the capacity. I wonder if we get that, and then I were to change it from like hello to he, if the capacity is still 5. Unless I like move out of scope, move into scope, which recreates it. I also wonder if I like push one character on, will it double the capacity? Like some things trying to do a linked list might like just double that as the way of like sort of giving me more space, or would it actually only add 1 capacity? Okay. We have that. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on a heap that the pointer refers to. In other words, the data representation in memory looks like figure 4.2. Well, meaning that if we have larger things like this, we can sort of copy this around, do lots of mutations with it, and that will help us. It'll help us like not use up too much memory if it's a large thing. The capacity will stay the same, but there is a method called shrink to fit that will return unused memory. Okay, so that's right. That makes sense. So if I have a really long-lasting function, and so it's not returning heap, and like I had a really big thing in there, it might be a really good idea for me to call that function just to make sure I'm not causing some kind of memory leak. But for the short term, I'm not going to be running into those problems, my guess, because I'm not going to be creating programs that require that big of memory, which is probably famous last words. The representation does not look like figure 4.3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 to equals S1 could potentially be very expensive in terms of runtime performance if the data on the heap was large. Yes, that's exactly what we were saying. But yeah, it's now pointing towards the same area in heap memory. Earlier, we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4.2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, there's one more detail that happens in this situation in Rust. Instead of trying to copy the allocated memory, Rust considers S1 to no longer be valid, and therefore Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. Okay, I want to try that. That seems foreign to me. All right, let's. What section am I in? I'll just do chapter 4. Okay, so let's take chapter 4, and in here we'll do cargo new dash bind, and I'll just call this examples. The name examples cannot be used as a crate name. Okay, guess not examples. Plain with strings. Okay, go to play with strings, cargo run to compile it, make sure it's working, and then code dot. Okay, so source main, close U. Okay, so the big thing that I want to sort of play with here is if I have let my string 1 equals string from, and I give it like hello world. I keep on doing that. World. Later. Then I do let, I guess I'm going to start with a print line S1. So given this, now when I run this, cargo run, okay, everything works exactly as expected. Then we say let S2 equals S1. We trim, ooh, yeah, so it already. Use of moved value S1. Value used here after move. Note move occurs because S1 has type standard string string, which does not implement the copy trait. Okay, so S2 is fine. It's just, okay. So I guess, is that for when I pass it into another function? I want to try that too. So if I have S1 here, but instead of doing like S2, what if I call a function which is like a print string, and we're going to pass it in S1. Yes, I know you don't exist. Also, so function print string. This takes a string, which is a can I just say a string? Doesn't return anything. Yep, unused. We'll print print. And this will be my string. Yeah, so that's not. Oh, it is. Use a moved value S1. So yes, that's exactly what the problem is here. That I'm moving S1 into the print string function. So it is doing the same exact thing as that equals, which now invalidates using this after this line. That's really interesting. So that will change how I have to think about programming here. Whereas if I want to just like print the string S1, it's not really going to work. Also, if I do something like this, let s2 equals s1, even if I say print s2, will that work? Yeah, still, like, I'm not allowed to do anything with s1 after this is done, because it's sort of like protected now and saying we've locked it up. You can't, you literally cannot do anything at all ever again. We would need to now say that this returns a string. Let s2 equals, and do it that way. Mismatch types. Expected, oh right, because now I would need to return the string. If you want to actually make a deep copy of everything, there is a .clone method. Ooh. So, so if I wanted to like copy S1 into here, so let's say I wanted to do this .clone like that. S1, I am not returning anything at all. Yeah, that seems to work. Also borrowing to the rescue, but you'll get to that. Yeah, that's my guess, is like that's the entire point about what borrowing is that I don't have to worry about any of this type of stuff, and instead like just borrow a read-only copy of it. That's the point of that. Okay, totally makes a lot more sense. Suddenly this now works. And then the borrowing is, string is going to be a what is it, str? And I think, is it just as simple as that? Yes. So now this also works. Yes. So yeah, that's the point about borrowing this. Or would this be called lending and this is borrowing? Or is that just too complicated and I'm just making it more difficult for myself? I'll probably get to it when I actually book covers it. I tend to do this a lot when I'm going through tech books. Okay, so we got this. We get this specific error. If you've heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer, length, and capacity without copying the data probably sounds like a shallow copy. But because Rust also invalidates the first variable, instead of calling this a shallow copy, it's known as a move. Here we would read this by saying that S1 was moved into S2. So what actually happens is shown in figure 4.4. No, S1 still exists, but like, does this amount get freed up from the stack? Because I'm assuming that it stores this information on a stack, which then goes into here. Representation of memory after S1 has been invalidated. That solves a problem. With only S2 valid, when it goes out of scope, it alone will free the memory and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. Ways variables and data interact. Clone. So that's exactly what we did there. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. We'll discuss method syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them before. Here's an example of the clone method in action. So yeah, we do this clone, and now we can work with them both. This works just fine and is how you can explicitly produce the behavior shown in figure 4.3, where the heap data does get copied, but is also very expensive. When you see a call to clone, you know that some arbitrary code is being executed and that the code may be expensive. It's a visual indicator that something different is going on. Stack only data copy. There's another wrinkle we haven't talked about yet. This code using integers, part of which was shown earlier in listing 4.2, works and is valid. Right, because when this is coming here, well, but that's because it's on the stack. But it's also creating a new section in stack from what I understand. But this code seems to contradict what we just learned. We don't have to call clone, but X is still valid and wasn't moved into Y. The reason is that types like integers that have a known size at compile time are stored entirely on the stack. So copies of the actual value are quick to make. That means there's no reason we would want to prevent X from being valid after we create the variable Y. In other words, there's no difference between deep and shallow copying here. So calling clone wouldn't do anything differently from the usual shallow copying, and we can leave it out. Rust has a special annotation called the copy trait that we can place on types like integers that are stored in a stack. We'll talk more about traits in chapter 10. If a type has the copy trait, an older variable is still usable after assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts has implemented the drop trait. Okay, so if something has the drop trait, it's assumed that it's on the heap essentially and that it needs to drop it. If a type has a copy trait, an older variable is still usable after assignment. Okay. But if it has, okay, so that's interesting. So you could have both copy and drop traits, but if you have the drop trait, things change drastically for it. If the type needs something special to happen when the value goes out of scope and we add the copy annotation to that type, we'll get a compile time error. To learn how to add copy annotation to your type, see Appendix C on derivable traits. So what types are copy? You can check the documentation for any given type to be sure, but as a general rule, any group of similar scalar values can be copy. And nothing that requires allocation or some form of resource is copy. Here are some of the types that are copy. All the integer types like U32, the Boolean type, bool with values true and false, the character type, all the floating point types, tuples, but only if they contain types that are also copy. All right, so that makes sense. Ownership and functions. The semantics for passing a value to a function are similar to assigning a value to a variable. Passing a variable to a function will move or copy, just like assignment. Listing 4.3 has an example with some annotations showing where variables go into and out of scope. Okay, so here's a full function. So we have let s equals, so we're creating a string from the literal hello. Takes ownership s. S's value moves into the function and so is no longer valid here. Oh wait, takes ownership is not a default function, it's here. Okay, so we call take ownership and we pass in the string. So it takes in some string, which is type string. It doesn't return anything. And then it just prints lines some string. Here some string goes out of scope and drop is called, the backing memory is freed. So that kind of makes sense. S's value moves into the function and is so no longer valid here, and then it's freed as soon as this function is done and removed from memory. So that's what's going on. Let x equals 5. So x comes into scope, makes copy because it's a, because it's just a copy type. Is that the right word? Is it copy type or is it the copy trait? I think it's just copy type, copy trait. So because it's just like a U32, an unsigned 32 integer, it's a copy trait. So when we call makes copy, it just sends a copy over to it. X is still valid here. Now, it says nothing special happens when it goes out of scope. Like, so when make copy finishes, some integer, I mean, I would assume that some integer is now removed from the stack. And then right here, X would be removed from the stack as well, so that they would no longer be valid. If we tried to use S after the call to takes ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Try adding code to main that uses S and X and see where you can use them and where the ownership rules prevent you from doing so. Well, it's fairly obvious. I mean, we kind of played around with this before with our projects, which is S is no longer valid after takes ownership. Like, that's just how it is. X would be. But that's because of the types and the traits that those types have. All right, return values in scope. Returning values can also transfer ownership. Here's an example with similar annotations to those in listing 4.3. Ooh, so returning transfer the ownership back to the original function. So if, before I even go through this, I want to play with this. So if I wanted to do this, less S1 equals this thing, not send a borrowed one, like send S, now I can do S1 equals, but I'm going to have to mutate it. This will take in a string and return a string. Yeah, so this also works just that same sort of way, because when we return it, it's again transferring ownership back to the main scope. And so now S1 has it again. But of course, if I remove the mute, it won't let me do that, because S1 has the previous version of it, lost ownership, and now would have to be shadowed again if I want to do that again. All these fun words to use with Rust. That looks like interesting. This looks like a lot of people seeing this from other languages would have a conniption. Why are you redeclaring it twice? And it's the same exact thing. We're just transferring ownership back and forth. All right, so let's take a look at what's going on here. In our main function, let S1 equals, so gives ownership. So we ask gives ownership, it's going to return a full string. This let some string equals the string hello, and then we return some string into S1. So S1 now has full ownership of it. S2 also gets like a very similar looking string, but it's somewhere else on the heap, even though it has the same data in it. S3 takes and gives back S2. That's exactly what we did there. It takes it in, it now owns it, it's completely invalid in main, but then it returns it. So now it's invalid here, goes away, but it doesn't really, because now main owns it again. Would I say that main owns it or S3 owns it? The ownership of a variable follows the same pattern every single time. Assigning a value to another variable moves it. When a variable that includes data on a heap goes out of scope, the value will be cleaned up by drop unless the data has been moved to be owned by another variable. So it's owned by variables. Taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. Sounds like we want to set up some kind of borrowing thing. It's possible to return multiple values using a tuple, like this. Sort of feel like we were naturally leading into borrowing, but we went into this instead. Oh, we've reached the end of this file. Okay. So function main, let s1 equals string from hello. Okay, so we create a tuple, s2 length. Oh, and we're destructuring it. So calculate length s1. We pass in, so we move s1 into calculate length, which then assigns ownership to s, but we're returning a tuple with string and usize. Let length equals, so we generate this, and we create just a number, and then we return the tuple. But this is too much ceremony and a lot of work for a concept that should be common. Luckily for us, Rust has a feature for this concept, and it's called references. Oh, I was hoping it was going to say lending or something. All right, so this was 4.1. Let's head over to 4.2, references and borrowing. The issue with the tuple code at the end of the preceding section is that we have to return the string to the calling function, so we can still use the string after the call to calculate length, because the string was moved into calculate length. I sort of feel that it's a little bit weird that they're referencing a completely previous sections when I can't see the code anymore because it was a different page. Kind of wish that they would put this all together. Here's how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership of the value. All right, so function main. So same thing, we're creating s1 and assigning it a string. Let length equals calculate length, and then send a reference to s1. And then we get the number back. So an unsigned, now I can't remember usize, is that sort of like creating the largest one or just one that seems appropriate as long as it's unsigned? And now this works. First, notice that all tuple code in the variable declaration and the function return value is gone. Second, note that we pass s1 into calculate length, and in its definition we take string rather than string. Well, we take I should have said a reference to a string rather than string. These ampersand are references, and they allow you to refer to some value without taking ownership of it. Figure 4.5 shows a diagram. So yeah, so we have usize is 32 bits. Oh, right. It's like the most appropriate architecture one. So, for example, this computer that I have right now is a 64-bit CPU with a 64-bit operating system. So it will work there. But I do like the fact that you can use 32-bit numbers in a 64-bit architecture. So I kind of like doing that, but I could see potentially if you're trying to be backwards compatible. For, let's see. All right, here we are. So S is right here. So all S is just the pointer towards S1, which itself has a pointer to where the actual data is. Note the opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator, asterisk. We'll see some uses of the dereference operator in Chapter 8 and discuss details of dereferencing in Chapter 15. If you dereference, does that take ownership? I kind of want to try, just because like we're talking about ownership and other things. All right, so let's come back and we're going to do, we have S1, we're going to pass into a function, print string. We're going to pass in a pointer towards S1, which this is now going to be a borrowed string. I am not going to return anything at all. Okay, so this is sort of where we're understanding it's working, but if I now want to do like let another string equals, and it's gonna be star string, then we do that. The trait bound str is not satisfied. Str does not have a constant size known at compile time. Oh, interesting. Okay, so I can't just do that. It's because as you were saying earlier, it doesn't pass over with the length, and it can't read that from the reference, I guess. That's interesting. Okay, so 10 minutes left. This is sort of like nice to know that this does not work. I'm looking forward to finding out more about this, I guess, in Chapter 15. Let's take a closer look at the function call here. S1 string from hello, calculate length, and we pass in a reference to the string. The reference S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference goes out of scope. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference. Let's add some explanatory annotations. Yeah, I don't really think I need those. This makes sense. The scope in which the variable S is valid is the same as any function parameter scope, but we don't drop what the reference points to when it goes out of scope because we don't have ownership. Functions that have references as parameters instead of the actual values mean we won't need to return the values in order to give back ownership, since we never had ownership. We call having references as function parameters borrowing. As in real life, if a person owns something, you can borrow it from them. When you're done, you have to give it back. So what happens if we try to modify something we're borrowing? Let the code enlisting 4-4 spoiler alert. It doesn't work. Of course not. I think I tried that quite a bit when I was first playing around with it. And that's where you all were sort of helping me go like, no, you can't do that. Also, I want to make it a thing that when you're passing in, that's called lending. It just sort of makes sense in the metaphor that we're using on this side of the function. I want to lend that function. Okay, so we create our string s. We call change and pass it and lend it s. Then in change, okay, we're taking in, we're borrowing string. And then, okay, some string push, like we attempt to change it, but because it doesn't know how long it is, it's not going to allow us to do that. Just as variables are immutable by default, so are references. We're not allowed to modify something we have a reference to. Mutable references. How long is this section? Oh, this seems decently long. So we have 7 minutes left. So I think what I'm going to do is sort of set this as where we're heading to next. So let's gonna close. I'm gonna save this and sort of like send this on up to GitHub. All right, so playing with strings, and I want strings with capital S. Strings, borrowing, and passing things around. All right. I have that, but before I commit that, I want to close this code window and come out to just learning Rust, and we're gonna update code here. All right, so currently at chapter 4.2, which is mutable references. Save that. I think there's anything else in here, so updated where we are at. All right, I'm pushing that up to GitHub right now. So I have a link to that in the description for this stream/video. And we can go sort of take a look at that, see what I did. There wasn't too much of the code exercises in this one, but we can actually see like where we're at and where we're going to continue tomorrow morning. Yes, I don't care there's an update right now. I'm not going to update this on stream. All right, I don't think there's anything else to sort of like work with here. We're I generally do this stream every single weekday morning at 7 a.m. Mountain Time. Thank you, Everest, for stopping by and taking a look. Thank you, everybody else who's either watching and sort of lurking here or watching the VODs and following along. If you are following along, I would love to know if you're also learning this along with me. So leave a comment in the video section. Also, feel free to leave an issue if you have a question in the GitHub repo, the Learning Rust one that I'm creating, or just sort of like a comment on how things are going. With that, that's all I've got. So unless anybody has a question or anything else to sort of chat with in these last few minutes, I think we'll call it a morning. Get on. Start moving on with our day. Which is perfect because I just finished the end of my morning tea right at the end of our stream. Okay, so OBS, there we go. With that, let's call it a morning, and I'll see you guys tomorrow. Have a great day.